Good evening. I would like to share with you some theoretical insights on possible mechanisms for nuclear fusion of hydrogen isotopes induced by lattice dynamics, and in particular so-called Phason flips in palladium and nickel nanoparticles. This outline shows you that first we would like to understand why the lattice dynamic is important, because it produces time periodic driving of the potential landscapes. And then we consider discrete breathers, which are nonlinear large amplitude vibrations in the solids, and in particular in using realistic potentials, we will see that they are possible in nickel and palladium hydrides. And the new thing is the Phason flips in palladium and nickel nanoclusters. Also, some phase diagrams of palladium and nickel nanoclusters loaded with hydrogen will be presented, and the relevance to the low energy reactions will be discussed. Well, first of all, shortly, why LNR is unbelievable from the mainstream science is because of the gamma factor, as you know, predicts that at the barrier of almost half MeV, you are going to, at the room temperature or near the room temperature, the probability of the fusion is 10 to minus very big number, is essentially 0. But the question is, however, is the Coulomb barrier that huge in the lattice? And as I noticed in my previous presentations, there were two major attempts to consider the influence from the solid state. One is Parrington and Lamb. Lamb is a Nobel Prize winner. And they actually were the first to consider electron screening. And as we know from the works of more recent scientists like Kasagi, numerous experimental works, that there is indeed screening from electrons, but the screening is maximum around 600 eV, which is very small as compared to half MeV we need to surpass. Another, and to my mind, more promising approach is to consider nuclear energy in atomic lattice and consider screening due to lattice oscillations, which was introduced by and proposed by Julian Schwinger, who actually considered for instance, two deuterons or deuterons and proton actually in the adjacent equilibrium position, but even at 0 temperature, you cannot suppress the quantum noise, which is 0 point vibrations, which in this case is around 0.1 angstrom. And when you calculate all the sums over the degrees of motion as he did, you actually obtained the effective barrier, Coulomb barrier. According to Schwinger, is expressed by this integral, which is reduced to usual Coulomb behavior only at large distances, but as the distances between the deuterons becomes lower or comparable or lower than the amplitude of quantum vibration, the barrier is saturated, and the saturation is around 100 eV. 100 eV is much lower than the half MeV considered for bare nucleus, let's say. So Schwinger actually estimated the fusion rate of this adjacent nucleus, and his estimation was something like 10 to minus 19 if for the nucleus sitting in the one cell and the one cell of palladium lattice, or 10 to minus 30 if two adjacent sites are considered. But what is more important even than these numbers are the very huge dependence or both on the, of course, of the distance between, equilibrium distance between the nucleus and more specifically on the amplitude of quantum vibrations, which is was estimated from the spectrum results to be around 0.1 angstrom. And of course, 100 eV is also a large barrier. And so the question is, can we increase the quantum noise? Similar to when we heat, we know that we increase the thermal noise, but can we increase the quantum noise? And in a textbook stationary state, one cannot do that because everything is fixed and the energetic levels are fixed for quantum oscillator, and we know this is a ground state. And then if you give a portion of energy, it's the first excited state, and you see the probability to find the particle in the bottom becomes 0, then like that, and you cannot do much about this. But if you consider a more relevant model of double well potential, which models actually some reactions, you need to go from this well to this well and apply time periodic driving to this potential landscape, then this motion can be actually viewed as two motions. First, the main one is that each of these wells like breathing. That this means the curvature, and that is the agent frequency of the quantum oscillator becomes the periodic function of time. And this problem then it can be solved actually analytically. And not going into details in formulas, the result is as follows. From the very narrow distribution of probability to find the particle in the center, with this increasing time of a number of these driving periods, you have more and more extended wave packet, let's say. At the same time, the energy is also increasing, actually exponentially. And this has some relation to the correlation coefficient, which actually was explained in many books by Vysotsky, but originally it was presented in some earlier works. What is important that if there's a correlation between the momentum and coordinate operators, then there's a construction called correlation coefficient. That actually the uncertainty principle is modified. And if correlation factor is close to unity, you can expect much larger fluctuations of energy and momentum, and as a consequence, even hope to make a barrier transparent. And this particular problem has an analytical solution, which we found 5 years ago. And indeed, this solution shows you that quite quickly the correlation coefficient in this harmonic potential can be very close to unity. But you cannot escape from the harmonic potential, infinite wells. So again, you have to consider double well potential. Well, there's a probability to find particle in one of the wells, and the transmission rate can be calculated. And this Schrödinger equation, it's possible to solve numerically in this case, not analytically. And then you show that starting from the initial distribution, in the stationary state, it becomes like this. It's almost stable. But when you drive it, you can see like the probability to find particle in the first well, initial well, decreasing, while this one is increasing. So you can expect this huge acceleration of tunneling rate. And what is interesting that the energy is almost constant in this case, and it is below the barrier. So it's we deal with tunneling, not with jumping over the barrier. And over the time domain, you can calculate the probability finding the particle in one well, another well. So you see this is jumping to and fro, only if you drive it. And the correlation factor is also can be calculated, and you see that in this case it's even not close to unity. But, of course, you should remember that this particular case was calculated when the barrier height was just 10 times more than the 0-point energy. And it's not the case with the Coulomb barrier for bare nuclears. But in the lattice, when we, if we take the expression from Schwinger theory, this integral expression, and just substitute instead of a constant amplitude of quantum vibrations, lambda 0, yeah? In Schwinger theory, it's just 0.1 angstrom. But in our model, when we drive the landscape, then it results in increasing of the amplitude of quantum oscillations, and as a result, this effective barrier, Coulomb barrier, decreases very noticeably. And you see, like here in 20 of cycles, actually you may deal with a kind of a barrier, or just a fraction around of 1 eV, which is practically chemical range. And of course, if you then substitute the same the same expression for the fusion rate in the Schwinger theory, you obtain a huge acceleration. Yeah, if you start from 10 to minus 30, you arrive to 10 to minus 9. Just because of this localization of vibration provided by lattice. All this preliminary consideration was done to show you the importance of time periodic driving of potential landscape, which, as we believe, can increase drastically tunneling and fusion in the solid state. And now we consider two examples. First is discrete breathers in periodic crystals, and then these Phason flips in nanocrystals. That's how looks the bulk of the palladium on nickel hydride. This is FCC lattice of NaCl type. And we apply usual molecular dynamic packets, lamps, so-called, with realistic potentials. And we can calculate, for instance, the density of states, vibrational states. There's an acoustic band, optical band, and between them there's a gap. So it means that you shouldn't find phonons, that's plane waves, in this frequency range. But if you then displace an atom strongly enough from the equilibrium position, then due to non-linearity, the frequency of this motion is a function of amplitude. And that's why this frequency can be controlled. And in this particular case, it results in the breather formation, which is persistent, for instance, here for 270 periods, atomic periods. So it's quite persistent motion. And this is a high frequency breather, 32 terahertz, which is well above the phonon spectrum. Yes. And also the result depends on the polarization, and polarization is 111, can produce even more robust breather, which is practically time periodic, and it lasts several thousand, almost 7,000 of periodical periods, atomic periods. And interesting that it's a gap breather, because the frequency lies exactly inside the phonon gap, so which explains why it can be so persistent, because there's no interactions with phonon modes. Do breathers exist at finite temperatures? It's a very relevant question, and it's not a simple one, because already at 100 K everything is moving, and at 1000 K moving very fast, and it's quite not so simple to find what is going on, and but it's possible to analyze the statistics. But the simple ways, just direct estimation of a number of high energy states, shows you that yes, there are, but very short-lived. It's around one period, you see? So it's just a fluctuations of energy, which not what we are looking for. But if we apply more sophisticated ways, it's called a wavelet analysis. And it first introduced by Professor Francesco Piazza from France. And he analyzed these dynamics of potassium iodide crystal. And this analysis is aimed in exactly detecting the dynamics in the specified frequency range, and then here is just an illustration. Some spots show you some rising excitations with the average lifetime here, dependence of the temperature, up to 1 picosecond, which is around 10 atomic vibrations. So it's not that much, but as we saw preliminary, even 10 periods can do a lot in times of potential driving. Another promising area seems to be to consider the dynamic of nanoclusters. And when you analyze the nanoclusters, the most interesting ones are so-called magic clusters, which have these closed shapes, yes? And they start from 13 and then 55, etc. And it's possible they can exist in two geometric states, cuboctahedral, and actually this will be the bulk structure, and icosahedral. And icosahedral clusters, it's actually the nuclear of the aperiodic crystals, yes, and because they possess the five-fold symmetry. And the question is, which of these states is more energetically favorable? And we try to address this with the means of molecular dynamics. A few remarks about the sizes. The minimum number is very small. It's just a half of a nanometer, its diameter. Yeah, I'm closing. When you consider its dynamics, at zero temperature, it appears that it can change from one geometry to another in a reversible way. So it's, again, we deal with the time periodic driving of this structure. And it's possible to obtain the Fourier spectrum and to analyze the main frequency of these vibrations. And okay, I will skip some of the animations. But it's interesting that at low temperature, at 0 K, it's very persistent, more than 100 of atomic scales. But as the temperature increase even to 30 K, then we see the decline of this time periodic phase transformation, and it becomes more chaotic. And at room temperature, it's chaotic from the very beginning. If you heat the crystal, the larger crystals, you can observe the transition from one structure to another. And then you can construct kind of a phase diagrams like this one, which shows you what to expect when you heat from cubic and or ICO phase, and depending on the number of absorbed hydrogen atoms. These are examples of such phase diagrams. And so in summary, we believe that the Phason flips, which are the phase transformations in the quasicrystal cluster, can be considered as a possible trigger of DD reaction or DH reaction. And we modeled this phenomenon using the packages of lamps for molecular dynamics, and validated it with ab initio, and also preliminary calculations show that these quasicrystals embedded in some mesoporous materials like zeolite also exhibit these phase transformations similar to what I have showed you. And so this may be concluded as a mechanism of catalysis in solids, which is based on time periodic deriving of the potential landscape, which can be induced either by discrete breathers, which can lower the potential barriers at high temperatures, or even increase the amplitude of zero-point oscillations, which can result in drastic enhancing of tunneling through the potential barriers. And a lot of outstanding problems, to mention just a few, that we need on the practical side, we need efficient methods to generate these discrete breathers in palladium or nickel hydrides in the materials of interest, let's say, such as electromagnetic radiation or electric pulses or other means of non-equilibrium state. And of course, we need experimental methods to synthesize very small clusters in the matrices, which is a very challenging task. Well, some of our works are presented here. And with this, I will thank you for your attention.
Thank you very much for this very fundamental research. Honestly speaking, I don't understand the majority of the subjects you mentioned. Just I understood that this breather mode allows to overcome Coulomb barrier.
Yes.
What is helps? What is how much the probability of reaction increases using this breather?
Well, this estimation shows you that without breathers, yes, just starting from Schwinger theory, for instance, there is 10 to minus 30, and with the number of driving periods, you can increase the probability by essentially 20 orders of magnitude.
Okay, and this mode is used in combination with some other approaches to increase probability.
Yes, absolutely. It's because it's based actually. It's a modification of the Schwinger theory, because this expression is derived by Schwinger, and what we add to it that we can show that the one of the key parameters, which is the amplitude of 0-point oscillation, can be increased by this time periodic driving. And this increase can increase the fusion rate.
In case this breather mode is used alone, can it help to overcome the Coulomb barrier?
I don't think so, because Coulomb barrier is huge, and so it's a combination of lattice dynamics, let's say, yeah. So you cannot consider breather without a lattice. Breather is in the lattice, and lattice assists even without a breather, according to the Schwinger model. Yeah, and then we further we make this increase even more. Yes. As I say, it's hard to imagine just a breather, because breather always exists in the lattice. And in the lattice, there's the main argument. We are dealing not with a just huge Coulomb barrier. We are already dealing with a screened Coulomb barrier. Yeah, that is the main argument by Schwinger. Okay, and then we can decrease it further. That's it. Okay.
So have you calculated how many orders of magnitude of enhancement of the fusion rate you get from the oscillating, the fluctuating potential compared to a not fluctuating potential? I think there's a paper by Kunin in 1990 that estimated about a 10 to the 8 improvement of the increase of the fusion rate from fluctuations, but I don't think they have done as extensive analysis.
No. It's a different mechanism, let's say. A lot of people actually consider the tunneling through the fluctuating barrier. Fluctuating barrier is not what we are considering, because when you consider the fluctuating barrier, the result is more or less understandable and very simple. Then if the energy of the particle to be transferred, let's say, is close to the barrier height, is close, then when this fluctuating is important, but it's not the case. It's not the case of nuclear fusion, because
in this case, kind of a combination with resonance effects.
Yeah, because in this case, yes, we deal with the energy which is much lower than the barrier energy. So what we consider is actually not a barrier fluctuation, but a fluctuation or rather driving of the well, which is important. Fluctuation of the well where the particle is sitting results in the spreading of the wave function. And then the tails of this wave function can be stretched to another well, let's say. So this is a different thing.
So do you have an estimate of the enhancement of the fusion rate?
Yes. This is a plot. This is a fusion rate. If you start already from Schwinger model, yes. For two deuterons sitting in adjacent sites, it's 10 to minus 30. And then you apply this driving And with each driving you higher and higher, and you saturate and around 10 to minus 9.
Thank you.
Well, what is the important role of a 0-point oscillation? What is the role of the oscillation? 0-point oscillation. Here. What is the important role of a 0-point oscillation? You said a 0-point oscillation. You need a 0-point oscillation, right?
Yes, 0-point vibration.
Vibration, oscillation.
Yes, oscillation.
So that makes sometimes makes a photon and sometimes distracted photon and so on. Just from a 0-point energy.
Yes, different energy. That was actually the main argument of Schwinger model. He considered the crystal at 0K.
Yeah.
0K. But still, even at 0K, it's a living thing. Yeah. Everything is vibrating with this small amplitude, 0.1 angstrom.
So in the other word, we can say that we can borrow the energy from a 0-point oscillation to increase the energy between the particles.
It's kind of not that simple. I think that it's not the borrowing of energy from 0-point oscillations, but the 0-point oscillations maybe is oversimplification, but it makes the it made the nuclear not that small as it used to be when it's bare nuclear. It's a 10 to minus 5 angstroms, for instance, yes? And when it's coated with these lattice vibrations, then its effective size is 0.1. And that's why actually the repulsion is saturated. That was the main argument of Schwinger theory, which I like. It's not our results, but that's our starting point. That's why we thought it was worthwhile to think, is it possible to increase this parameter further? And probably we can.
Okay. Any questions? Okay, ask. Okay, please.
Is it possible to calculate how close the protons have to get to occur the reaction?
Is it possible what?
To calculate the distance, how close the proton has to get to each other to be sure the reaction occur?
I think that no, because due to this uncertainty, etc. You see, you can just calculate the probability of reaction, but not the exact coordinate or whatever, because it's a quantum world and everything is uncertain. But the result is known, let's say, in probabilistic terms. Yeah.